Hello, my name is Yu Li. I work for Vanitec as a technical officer. And today, I'm going to talk about welding heat effect zone toughness of vanadium microalloyed steels. Microalloyed steel has been widely used for structural applications such as buildings, bridges, offshore platforms, and automobile components. However, the balance of high strength and good toughness in microalloy steel can be upset by the thermal cycles experienced during welding, producing areas of poor toughness known as local brittle zones. The most critical part of the weld joint is the coarse-grained heat effect zone in single-pass welding and the intercritical reheated coarse-grained heat effect zone in multi-pass welding. This presentation will concentrate on the weld heat effect zone toughness of vanadium microalloy steels. This slide shows the local bright zones in single-pass welding. And for single-pass welding, the local bright zone is coarse-grained heat effect zone. You see is the red color part. And the coarse-grained heat effect zone during welding experience peak temperatures up to the melting point, followed by cooling. The cooling rate is dependent on welding heat input. The high peak temperatures can lead to significant austenite grain coarsening, and the combination of a coarse austenite grain size and rapid cooling promotes brittle microstructures such as ferrite set plate, you can see here, and also upper bainite. The coarse-grained heat effect zone toughness is controlled by the heat effect zone microstructures. This is a function of steel composition and weld thermal cycle, especially the welding heat input. For example, promoting intragranular acicular ferrite, which has high resistance to propagation of cleavage microcracks, is beneficial to coarse-grained heat effect zone toughness. This slide shows the effect of vanadium on the toughness of grained coarse heat effect zone. This is very early classic work published in 1970s. So from this figure, you can see addition of vanadium up to 0.05% was beneficial to the coarse-grained heat effect zone toughness, particularly at lower heat input. For high heat welding heat input, the coarse-grained heat effect zone embrittlement occurred for vanadium content over 0.1%, and for low heat input, up to 0.25% of vanadium could be used with no detrimental effect on the toughness at both low and high nitrogen contents. Since the 1970s, there are so many published work to show the similar trend in respect of the influence of vanadium on the heat effect zone toughness. So this slide shows another example of the influence of vanadium on coarse-grained heat effect zone toughness. So you can say you add vanadium 0.05%, so that's actually beneficial to the heat effect zone toughness. But if you increase the vanadium content to 0.1%, decrease the heat effect zone toughness. So from this slide, you can say what effect vanadium on the toughness of grain coarse heat effect zone. So on the top, this micrograph is for carbon manganese steel. On the bottom, this micrograph is for 0.05% vanadium steel. So you can see the difference. In the carbon manganese steel, they're more like a set plate microstructure, and the grain bonded ferrite is quite, is straight. And you see the vanadium steel, you got more acyclic ferrite and less ferrite set plate. And you can see the difference between the two steel for the green boundary ferrite. There are so many small greens for the vanadium microalloy steel. So many publications demonstrate that vanadium promotes integrated acyclic ferrite and polygonal ferrite transformation. And also vanadium reduces the effect grain size, which is the main microstructure feature controlling the cleavage crack propagation. Changing green boundary ferrite morphology from films in the carbon manganese steel to polygonal in vanadium steel, which have more resistance to crack propagation. The enhanced green boundary ferrite nucleation in the vanadium steels can prevent magnetic formation and benefit integrated ferrite. Also, vanadium in steel can reduce free nitrogen level in the matrix. Therefore, vanadium can improve coarse grain heat effect zone toughness. This slide shows the effect of nitrogen on the toughness of grain coarse heat effect zone in vanadium-containing steels. Nitrogen is an important element in vanadium microalloy steel for precipitation strengthening. Carbon manganese steel with high nitrogen content is generally expected to have low heat effect zone toughness because of the free nitrogen. The effect of nitrogen on the heat effect zone toughness in vanadium-containing steels is dependent on the weld heat input. At a low heat input, the effect of nitrogen is small. As shown in this slide, you can see. At high heat input, high nitrogen could result in poor heat effect zone toughness, and a controlled small addition of titanium to vanadium-containing steels can be beneficial to the heat effect zone toughness, especially for high heat input, since nitrogen combines with nitride, nitrogen to form stable titanium nitride particles, which prevent alternate grain coarsening in the heat effect zone at peak temperatures. So this slide shows the work by Swedish Institute for Metal Research, and it demonstrates that high nitrogen vanadium titanium can have excellent heat effect zone toughness when the heat input is lower than 4 kg per millimeter. So you can see here. And at high heat input, so high nitrogen steel actually have worse toughness than the low nitrogen steel. This study indicates that good heat effect zone toughness of the high nitrogen steel for low heat input welding is associated with the promote intragranular nucleation of ferrite. And the green boundary ferrite is responsible for the poor heat effect zone toughness in the high heat input welding. So this figure shows again the effect of nitrogen on the toughness of coarse grained heat effect zone in vanadium-containing steels. This work is carried out by Sidri. It was a Vanitec project. And you can see the vanadium, titanium, and nitrogen steel exhibits the highest heat effect zone toughness for all the range, the heat input they used. And the author suggests that the improved heat effect zone toughness is associated with the changing of coarse grained heat effect zone microstructures from coarse ferrite with a second phase plus ferrite set plate. You can see in this figure. That is the titanium vanadium steel with low nitrogen. And compare that figure, compare with this micrograph with high nitrogen. So here you can say is more ferrite side plate or upper bainite. And here you see lots of more intergradient nucleation, ferrite, acyclic ferrite, and polygonal ferrite. So the change, the microstructure from here to here is responsible for the high toughness in the high nitrogen steel. And now we're talking about the multipass welding. For the multipass welding, the local heat effect zone is the intercratically reheated coarse-grained heat effect zone. So you can say here, this zone is the coarse-grained heat effect zone reheated by the subsequent welding cycle. So this zone is heated to the ferrite and the austenite two-phase field and then cooled. So the reformed austenite actually is a preferred nucleate on the austenite green boundary, you can say here, and also on the Vanitec Ltd boundary or on the carbon-rich area like pearlite. And during the cooling, with quite fast cooling rate, those austenite formed in the intercritical field will transform to IMA phase. And because the austenite green boundary was really rich in carbon, so those reformed austenite is rich in carbon. And during cooling, some of them transform to twinned martensite. Those IMA phase is really hard and brittle. This slide is the ICM Graph showing an initiation from the IMA particles on fracture surface of sharpie impact specimen. That's the initial site. And that is the IMA particles on the perennial austenite green boundary. You can see that they are already cracking. So this is solid evidence of how important the IMA particles in the intercritical coarse-grained heat effect zone for the toughness. So this slide shows the effect of area fraction of IMA phase in the heat effect zone. So you can say the effect of how many IMA particles in the heat effect zone. You got more IMA particle, you will have low toughness. And also from this figure, you can see these two green. They are vanadium-containing steels containing 0.05 vanadium. They have better toughness than the carbon manganese steels. But if you increase vanadium steel to 0.1%, that's that two circles. So you decrease the toughness. And the right one is niobium steel. This slide, you see the effect of the size of IMA phase on the intercritical coarse-grained heat effect toughness. So this figure is the effect of the maximum size of IMA particles, and that is the Sharpie transition temperature. So you can see the effect. If you got really big IMA phase, that particle will crack first and initiate the big cracking. So result, final failure. So the average size of IMA particle on the heat effect zone toughness. So you can say the average particle size has less effect than the maximum size of IMA particle on the heat effect zone toughness. And this slide shows the vanadium on the intercritical heat effect zone. This slide shows the effect of vanadium on the intercritical coarse-grained heat effect zone toughness. So you say, the bottom one is actually the coarse-grained heat effect zone, and the top one is for the intercritical coarse-grained heat effect zone. The first thing you can say from this figure is the intercritical coarse-grained heat effect zone, which has the heat effect toughness than the coarse-grained heat effect zone for multi-pass welding. Second, you can say the effect of vanadium. So for both zones, you say you increase vanadium content from to the 0.05%, you improve the heat effect zone toughness. But if you increase the addition to 0.1%, and which result in lower toughness than the carbon manganese steel. And this slide shows the effect of vanadium on the IMA phase in the intercritical coarse-grained heat effect zone. So you see from this figure, that is just for the peak temperature. The second peak temperature is 750 degrees C, and this side is for the second peak temperature of 800 degrees C, and that green is for area fraction of IMA phase, and the red is green boundary with IMA phase, meaning it's the outside green boundary with IMA phase. And the pink one is the average size of IMA phase, and the blue one is the maximum size of IMA phase. So you can see the vanadium effect. The first, you say the 0.05 vanadium steel, which have the lowest green boundary with IMA phase, and also which have the smallest maximum size of IMA phase. I think that the addition of microalloying have big effect on the maximum green size and the green boundary with IMA phase, but less effect on the area fraction of IMA phase and the average of IMA phase. Vanadium microalloy steel are readily weldable and can accept improved heat effect zone toughness. Vanadium promotes intragradually acyclic and polygonal ferrite transformation and reduce effective green side in the coarse-grained heat effect zone. High nitrogen vanadium microalloy steels can have good heat effect zone toughness by careful selection of micro additions and welding parameters. The addition of 0.05% vanadium to carbon manganese steel inhibits IMA phase formation and is beneficial to the intergradually reheated coarse-grained heat effect zone toughness. The positive effect of vanadium on the intergradually reheated coarse-grained heat effect zone toughness become negative at vanadium level higher than 0.1%. Thank you very much for your attention.